train, whatever, get them here, they get to the end, right? So just keep that in mind when we talk about pathways. It's just a pathway like this. You're familiar with it. So what we could do is, let's say I had a mutant that's defective in this step. D should build up. If I gave it C prime, would that rescue it? Would it allow it to get to the end? No. But would E or F? Yes. So chemicals downstream of the block will rescue it, and chemicals upstream will not. That's going to be important. We are going to look at various mutants and we can figure out the entire pathway by knowing that chemicals downstream of the block rescue it chemically, and things upstream don't, and knowing that this builds up. Any questions about that? What accumulates and what rescues? Okay, let's move on then. So as we said, these chemicals could rescue it, these could not. But we're going to do a genetic rescue. We could do a chemical rescue, but we're going to do a genetic rescue. So what we're going to do is we're going to make diploids, which means we'll have two sets of information now. So let's look at cross one. Okay. Now, you do not know the genetics ahead of time, but you will know it from the information, okay? And I did not make this definition. It is the only one that works, but it's confusing. So let's look at this cross one. We have a known mutant here with another mutant. The steps are in two different paths. Would these rescue each other genetically? Yes. Let's watch why. So genetic information says, okay, I can convert C to D. This piece of information says, no, you can't. But this one says, yes, you can. So D gets made. And then this genetic information says, I can't convert D to E because that enzyme's not functional. But there's a second gene, because it's diploid, that's functional, that encodes the enzyme that converts D to E, so I can get to the pathway. So genetically, by making this diploid, by themselves, the haploid can't grow. They need histidine. So if I want to look at them, I have to get a medium that has histidine in it to allow them to growth. This one can grow on histidine, supplemented medium. When I make them, if I put them on plates that don't have histidine, would these things grow? This cross one, would they grow? Yes, because they make histidine, now they can grow. So these two would complement one another. Now let's look when they don't complement. Cross two, since the defect in the genome is the same enzyme, we build up D, but we can't make E. So would they grow on a plate that lacks histidine? No. So they would fail to complement. Now here's the definition. Write this down. A complementation group are those that fail to complement. That's right. Somebody said what? So I'm going to do it again. A complementation group are those that fail to complement. Seems backwards. When we do some more of this, you'll understand why this definition is the only one that works. So a complementation group are those that fail to complement. Now I'm going to show you how easy this is to do the actual analysis. What you're going to do is we're going to give you a known strain of mutants. They will precipitate out very quickly. So you just vortex them, hold the tube when you put it on the vortex, or the tube goes flying, hold the tube, that'll cause the yeast to go back in suspension. You're going to then take a loop. You've been working with these. You're going to use the circular end now. So this is a large scale of that loop. You stick it in the tube. The yeast get transferred to this. There's no mesh, but there's enough surface tension and capillary action that you form a thin film of water here, the buffer with the yeast, and then you put it on the auger. Now you know that the auger is the gel part. You don't want to do this because that just digs the auger. So to transfer it, you literally go like this. You see a lot of digging. Don't do that. Flip it like this. And you have to put a little pressure. Now, this isn't going to bend, but these are plastic. So put a little pressure, that will bend. That will allow the entire surface to make contact with the plate, and then slowly pull it. If you pull it like this, there's no solution there. It's all here. You want to go slowly like this. You'll transfer that 10 microliters and let it dry for about 10, 15 seconds. Hold it out like this. Don't start tilting it. Let it dry a little bit. And then you should see a cloudy line. If you see a cloudy line, you have enough yeast. If the cloudy line's only at one end, take another sterile loop and streak it. But it's important that you have enough yeast there because we're going to mate them. Okay? So that's with 10 microliter loop. To do the matings, as I said, if they touch, they mate. So we're going to take a second tube, like M1 or M2. We're going to vortex it. You go in with a loop again, and you streak it across. So as you view this, to the left, halfway there. But the moment they touch and go over, they're diploids because they mate. Now these are chosen such that this is all alpha and these are all A's, so they'll mate. So the moment they touch, you created the diploid. The moment they touch here, diploid. The moment they touch here, diploid. The moment they touch here, diploids. So to the right should be diploid matings, results of mating, and to the left, haploids. So what we'll do is we'll then take these and grow them on plates that don't have histidine. Now they grow fine on. Sorry, let me rephrase that. We'll grow them first on plates that have histidine, so everything grows because there's no selection yet, right? So there's histidine in the background, everything grows, but then we'll somehow transfer them from this plate to a plate that doesn't have histidine, and then we can see do they grow. So the next illustrates this. This is a plate that we streak down like this and then across. Now, it didn't look like this when we first did it because the yeast weren't colonies. Here we have colonies that touch, so we grow them up. So it looks a little cloudy, 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 cloudy. We grow them up, and since there's histidine here, everything grows because we give it in the background. Even though they're mutant, they can still grow. Now, what we'll do is somehow we'll transfer them to this plate. Now, I usually wear a jacket and lean against the board here, then turn around and you see the number 14000 written on my jacket because the nap of the fabric picks up the chalk. So we're going to use velvet, sterile velvet, and we're going to just push the sterile. We have a tool, and we'll push the sterile velvet onto the surface. That transfers the yeast from the plate to the velvet, and then we'll use that tool to transfer the yeast onto this plate. So when we first do that, we see a little cloudiness, but not this kind of growth. So that's called replica plating, used all the time. It's like a carbon copy of these cells onto here, and then this does not have histidine. So they can only grow if they complement, genetically rescue one another. And we see this as a lot more growth on this side versus this. So this is about the same on each side, so did they complement? No. They failed to complement, which means what? They're in the same complementation group. The ones that fail to complement are in the same complementation group. I'm going to stress that because it's not the definition I would have chosen. And these complement, okay? Which means these had defects in different genes, and these had defects in the same gene, okay? Okay, so anyway, you're going to vortex. You see nice cloudy line. Then you're going to streak across. These represent the diploid, okay? And now let's quick look at this, and then I'm hoping to get my symbiosis. Be very quick though. So let's just do this. You can figure out the order of the pathway and the number of genes involved. So let's look at this. The minus means they failed to complement. The plus means they complemented. This is 1 with 1 will always fail to complement. 2 with 2 will always fail. That's why we have minuses this way. But 1 and 2 failed to complement. So are they defects in the same gene or different? Same. When they fail to complement, they're in the same complementation group, same gene. So how about 1 and 5? Do they complement or not? No. So 1, 2, and 5 are in the same complementation group because those failed to complement. So from this information, we know now that represents 1 gene. Those 3 are in the same complementation group because those 3 failed to complement. But I don't know anything about 3. All I know is different than 1, correct? I know it's different than 1 because it complemented. But what I don't know is 3 in the same complementation group as 4 or 6 or whatever. I don't know. How can I find out if 3 is in the same complementation group as 4? Make them. So let's look at this. 3 with 4. Do they complement? Yes. So they're different. So I know 3 and 4 are different. How about 3 and 5? They complement, so I know that's different. But I don't know about in about 4 and 5 yet relative to each other, right? But eventually when we see this, we see that 3 and 7 failed complement. So what are they? In the same complementation group. They lack the same information. So how can I find out about 4 and 5? What would I do? Rate them. And what do we see for 4 and 5? They complement, so I know 5 is different than 4. And we still have to do 6. 4 and 6 complement, so I know 6 is different, but do I know about 5 and 6 yet? No, how would I find out? Rate them. What do we see for 5 and 6? They complement, so they're different. So I now know there's one genetic locus, a second genetic locus, a third, a fourth, and a fifth. So there are at least 5 genes in this pathway. Now, you know, so here's gene 1 is a complementation group, a second complementation group, a third complementation group, a fourth complementation group, and the last one, the fifth. So there's at least 5. Is that right? Did I do the math right? Oh, sorry, you're absolutely right. 5 was there, so yeah. So there's 4. Yeah, 5 was already in the first group. Okay. Now, you can actually figure out the order of this. I'm going to let you think about that. We'll go over this next week because I do want to get to mitosis. Figure out if this rescues, remember, it's to the right of the path, right of the block. So right now we know for sure, I'll just do 1. We know that in 1, 2, and 5, C accumulates. So we know for sure it's like this. C is here, and it's blocked, and that's mutants 1, 2, and 5. Okay? Because C accumulated, and then it's rescued by A, B, and D. So A, B, and D are to the right because it rescues. Let's just do one more. Let's do mutant number 6. It accumulates D, it's rescued by B. So we know for mutant 6, it's like this, and that was mutant 6. Because D accumulated, and B rescued. Rescues to the right, accumulates immediately to the left. So we now know B and D is here. We just got to figure out where A is, right? So I'll leave that for you, okay? So let's get to the mitosis and meiosis stuff. A few reminders of this. Ploidy, number of sets. So when you play with a deck of cards, there's 4 suits. Hearts, ace, diamonds, spades. Those are the suits. Those are the ploidy. But there are 13 types of cards. Chromosome structure. We'll go over that. It's composed of DNA and protein. Genes and loci, we've gone over that. Mitosis, meiosis. I want to stress right now, with meiosis, there will be 2 divisions of the DNA. Mitosis, only 1. Both cases, there's a duplication of DNA. So if you double the DNA and then divide it once, you get back to the same amount of DNA. That's mitosis. You don't change the ploidy at the end. But with meiosis, you have 1 duplication, but 2 divisions. So just like math, you have to half the number. So meiosis changes the ploidy. Okay? We'll talk about interphase, where mitosis is not occurring, the DNA is usually stretched out. We'll talk about prophase, where the DNA starts to condense. Your book has a lot of animations on this. I'm not going to have much time to go over this. But in prophase, the DNA starts to condense. In fact, historically, we say prophase is occurring because we can see visible chromosomes with a light microscope. Okay? So prophase is when we start to see chromosomes visible in a light microscope. We usually have added dyes to it, and they're condensed. What happens is, we see here, it's just labeled here, centromere, that's where microtubules attach. These microtubules will generate forces and push and pull chromosomes to a middle line, and then actually separate them. Okay? So we'll go over that. Remember the life cycle. Gametes, meiosis produce haploid gametes, fertilization, diploid, and then mitosis here. Okay? So we still have 9 minutes. Gene 1, gene 2, gene 3. This is the chromosome. It's actually packed with proteins, but remember this information here. This shows you highly condensed. Now it shows you as chromatids here, because this is the way it works. And I'm going to do this with my hands because I think this works well. One of the students, quite a few years ago, he teaches at UCSF, med school there, and he still has to do this 5' 3' stuff with the med students at UCSF, and he still does this with mitosis and meiosis. So even though you may think you may know this, sometimes, I grabbed the wrong size gloves. So I don't have 23 pairs to do this. So this is chromosome number 1 from mom, chromosome number 1 from dad in a somatic cell. And there are 23 of these for a total of 46. Okay? So during interphase, these things exist. They're stretched out. Then during S phase, I will duplicate the DNA. So S stands for DNA synthesis. It precedes meiosis. Again, 1 duplication, 1 division mitosis, 1 duplication, 2 division meiosis. So we end up with chromosomes with sister chromatids. Okay? Now these are not visible at this stage because during S phase, they're really stretched way out. Okay? They're stretched way out. As they start to condense, they become visible. Okay? So whenever you see a chromosome looking like this, that's because there are 2 chromatids and it's highly condensed. This is what it looks like oftentimes when you see like a scanning electron micrograph of it. They look like this, has a sort of topology to it. So there's a chromosome with sister chromatids, chromosome with sister chromatids. These sister chromatids are effectively genetically identical because it was taking the DNA, and it's kind of like PCR, but there are some differences. It's taking the DNA along the entire chromosome and separating it in many places and eventually making an exact duplicate. So that's the chromosome with sister chromatids. They are effectively identical, but there are a few mistakes made, but we call them identical, okay, in terms of that copying. So we have chromosomes like this with sister chromatids. During prophase, they're highly condensed. During prometaphase, those microtubules have attached. The nuclear membrane has broken down, which allows the microtubules to go into formerly the nucleus, right? So it allows them to attach, and then they generate forces. And they're on each side. So the forces align like this. This is mitosis, not meiosis. Mitosis, I have 46 chromosomes on line like this. Each of those chromosomes consist of identical sister chromatids. During metaphase, they're lined up. Prometaphase is where they're jacketed in place. So metaphase, middle, meta, they're lined up like this. Anaphase separates the sister chromatids. Okay? So ana, like analysis, to separate. So anaphase separates the sister chromatids. During telophase, we'll reform the nuclear membrane, and then we'll get cell division or cytokinesis. So what we end up with are 2 cells genetically identical to what we started. Okay? 1 duplication, 1 division. All right? So can I get my volunteers? Can you get your gloves? All right. Now I'm going to do meiosis while we have biology taking place. Now we're doing meiosis. This is different. Again, 1 duplication. But in this case, homologous chromosomes pair up. Write that down 3 times. It's that important. Homologous chromosomes pair up. That's unique to meiosis. So now I have 23 pairs lined up. Right? Because I had 23 types, now I have 23 pairs. So in meiosis, during prophase 1, I now have to give it numbers because there's 2 divisions. During prophase 1, they condense. Prometaphase, they lined up in the middle. Now, metaphase 1, they're lined up. During anaphase 1, I separate members of this homologous pair. Not sister chromatids, but actual entire chromosomes. Okay? All right? And this is chromosome pair number 1. Come on up. Okay. So now in this cell, we're going to have 4 chromosomes. Sorry, 4 types, 8 chromosomes. I got to watch the biology. Okay, hold the fingers. Not yet. We haven't done S phase. Now do S phase. Now we're duplicates. Homologous pair, same genetic loci, may or may not get the same information. Homologous chromosomes may or may not get the same information. If it's the same, it's homozygous for that locus. If it's different, heterozygous. And any other homologous pair, okay? So let's do mitosis. So chromatophage, we line up in the middle. Yep. Yeah. Tell you what, why don't we do it this way? This is going to be easier, okay? We're going to do it this way. And then we separate, right? And then I give a chainsaw, knock it down the middle. And there's a exact number that we started with on each side, right? There's 8 on each side. Now let's do meiosis. So let's go back. S phase. Prophase 1. I pair up. Homologous chromosomes pair up. I'm not pairing up over here, right? Only homologous chromosomes pair up. So those 23 specifically pair up. I have 20 homologous pairs. Prometaphase. You line up in the middle. Yep, okay. Then we separate. Now, it just happened by chance we have all blue on this side, right? And all green on that. But I could have done this, and we have that, right? So these chromosomes can line up independently on this metaphase plate. So we'll get random segregation of chromosomes. And likewise, what I haven't shown you is I'll do this, and then I'm going to get a volunteer. He has the highest pain tolerance, so he'll be the volunteer. So it goes like this. Duplicate. But what's unique to meiosis is crossing over, right? Where they can physically exchange the DNA. So I don't want to cut my own fingers. It's okay. So I'm cutting the DNA. You can't see this. But there's a little piece of, it's not lost in the cell. There's a little there. And then over here. And then I take this blue piece, and I exchange it over there. And this one here. So I literally physically exchange the DNA. But that can happen multiple times along a given pair, and as we do this. So that's what recombination is that random exchange of DNA. Okay, so thank you. But let's quick go over a few things in terms of the diagrams. Meiosis is probably one of the most difficult concepts to really grasp, okay? And that change of ploidy in C. So let's just do a few things to help you understand this, okay? So I'm going to refer to this value as C. Probably none of you have ever heard the term C, but it's going to help keep things clear. So when I have a cell like this, it's 2N, 2C. It's 2N because there's 2 sets. And we can say the gamete, which has only 1 set, I'll call the gamete artificially 1C. I could call it half C, but it gets confusing. So we'll just say the gamete is 1C. It's the amount of DNA. I can measure it by fluorescence. I can measure it by weight. I can measure it by number of base pairs. So that gamete is 1C. So when I have this cell that's 2N, it's 2C, correct? Does that make sense? It's twice as much DNA. 1 set sperm, 1 set egg. This is 1C, 1C. When I get fertilization, 2N, 2C. When I duplicate the DNA, have I gained any new sets of DNA? Have I gained any new information? No. I have not changed the ploidy. It took me 8 years to get the biology books to get this right. They would always say you change the ploidy when you duplicate the DNA. You have not. There's no change in ploidy. But you have changed what? The amount of DNA. So this then is 2N, 4C, right? Still 2N, but now it's 4C. When I pair up, still 2N, 4C. But the moment I separate these and form new cells here, I've changed the ploidy. It's now haploid, right? There's only one member of each of those pairs. So that first division reduces the ploidy to 1N, but 2C. And remember, mitosis separated the chromatids. So the second division of meiosis is identical to mitosis. You separate the sister chromatids, but in this case, there's half the number of chromosomes, and there may have been recombination, okay? So draw that out for yourself. I think it will help you understand, okay? So enjoy the lab. It's a lot of concepts to introduce.